Good morning, guys. We are going to finish up the last couple types of problems um, with limits and some special types. Yesterday, we did asymptotes. We did when it's greatest integer. Um, so today we're going to do a few other special types. All right, and then we put these all together, and then the hard part is looking at an equation being like, oh, this is what the method we're going to have to use. And then we'll spend the next few days reviewing all these and practicing a bunch. All right. So here we go. All right. So the next type is what we call a rational absolute value. What is a rational absolute value? Well, rational means a fraction, and absolute value is what you would expect, an absolute value. So this is an example, the absolute value of x minus 2 over x minus 2. Of being a rational absolute value. Now, the reason this is a special thing and where we just, obviously we can't just plug in 2 because we get 0, is because if we actually did these when we put these in our calculator, the first thing we did with limits, these graphs are like long lines like this. And we have to check to see if we're at a jump, because if we're at a jump, obviously it will have a different limit from the right and left. If we're not at a jump, it's going to have the same limit, and we can figure that out. So what we're going to do is very similar to what we did when we're at an asymptote, where we're going to plug in something a little bit bigger and a little bit smaller. The only difference is we're looking for the exact number value, not just if it's positive or negative. So it's positive or negative infinity. All right. So if I'm just going to plug in something a little bit bigger than 2, we're going to do the same thing we did before. We're going to do like 2.1. So 2.1 minus 2, the absolute value of that, over 2.1 minus 2. All right. So 2.1 minus 2 is going to be 0.1. So the absolute value of 0.1 over 0.1 is 0.1 over 0.1, which is just 1. So I care about the value. I don't care about like just that it's positive. All right. I'm looking for an actual number here. If I do the same thing, but from the left, I'll do 1.9. The absolute value of 1.9 minus 2 over 1.9 minus 2. So 1.9 minus 2 is negative 0.1. All right, but the absolute value of negative 0.1 is positive 0.1 over negative 0.1. Well, that's not positive 1, it's negative 1. All right. And since these are different, you could probably guess that the limit is D and E. If they were the same, that would be the limit would be, if they're both 1, then the limit would be 1. If they both were negative 1, the answer would be negative 1. In this case, it does not exist because they are different. So anytime you see a fraction with an absolute value in one place, this is how you're going to approach it. All right. Now, we did one the first day of a multi-rule function. All right. And it was similar to this first example where we're going to do x is approaching 5. So we look here and we are going to plug into this equation because 5 is greater than 3. All right. So I do 3 times 5 plus 1. I get 15 plus 1. The answer is 16. So if it was anything less than 3, you would plug in here. Now, the question comes when we have something like this one right here. The limit of f of x as x approaches 3. Do you see how 3 is this number right here? And you might be like, well, I should just plug into the top one because it says greater than or equal to 3. Well, the thing is, I need to know if I have something that looks maybe like this. If there's a jump at 3, if they're connected or not. If they're connected, it means there's going to be a limit. If they're separate, they're not connected, that means there's not going to be a limit. So what you have to do with a multi-rule 1, where you're finding where x approaches 3 and 3 is like where it splits up, you have to plug into both. When I plug 3 into this one, I get 10. When I plug 3 into that, I get 7. Since they're different, the answer is D and E, does not exist. If they were the same, that would be the limit. They were different, so it's D and E. So for a multi-rule, when you're approaching a value that we have that's the dividing point, you plug into both. If it's just one that's not this number, then you plug into only one, and that is your answer. All right. So all these are just like little special ones. And like I said, we'll practice a bunch of these. Now for this one, it's square root. Now, let's say let's forget that this was 3. Let's say I made this 4 and just substitute it in. You get the square root of 4 minus 3, which is 1. Square root of 1 is 1. 1 would be my answer. Nice. But I don't have that. I have 3. And you might still think, well, if I plug 3 in there, I get 0, and the square root of 0 is 0. All right. But what you have to be careful of is 3 is like the endpoint of this graph. If we remember from graphing square roots, all right, this 3 zeros here, and it's pointing to the right. So if I was to say what the limit as x approaches 3 is, well, from the right side, it's 0, but there's nothing over here to the left, which means what's the limit? Does not exist. So when you plug it in, if you get 0 in here, that means it's most likely that is going to be your starting point or end point of your graph, however you're thinking about it, which means the limit does not exist, right? But if I had 4 like I did before, that would be okay, because if I pick some random point up here from the right and from the left, I'm going to the same y value. It's when it's at the end point and there's nothing to the left of it, or could be to the right of it. The limit does not exist. All right. So all of these are like special little things that when we, almost have little special rules to themselves. And when you notice them, you just have to be careful. All right. All right. Last thing is trig. Okay. Now, the easy thing about these trig problems are going to be finding the answer. The hard part is showing, not that it's hard, but the harder part, I should say, is showing why it is. And you have to show work for these problems. Now, this thing I'm boxing right here, this is important. All right, this property. What this says is that the limit as x approaches 0 of sine of x over x, or of x over sine of x. So whatever comes after sine has to be there, has to be on the bottom. If that ever happens, the limit is always 1. All right. So the limit of sine of x over x as x approaches 0, or the limit of x over sine of x as x approaches 0. Those are both equal to 1. All right. And that's going to be a very important property for us to remember. All right. Now, so here we go. The limit as x approaches 0 of sine of 4x over x. I want to manipulate this so it gets some form of this property in there. And the way I'm going to do it is this. I am going to split up my two things. I'm going to put sine of 4x. I'm going to make two fractions out of this. And then I'm going to put, I'm going to put sine of 4x over there. All right. And I put x here. And you can put x over here, but we'll just keep this. Now, this is not equal to 1. It almost is equal to 1. But in order for it to be equal to 1, I need whatever is after the sign to be underneath. I have a 4x here. So in order for that to equal to 1, I need to put a 4 there. But I can't just add a 4 to the bottom of something. But if you multiply the bottom and the top to something, you can. All right. So now the limit as x approaches 0 of this. This is all what I have boxed in pink here, or red, whatever color this is. That is all equal to 1. And then I have times 4. What's 1 times 4? 4. The answer is 4. All right. So I manipulated by multiplying the bottom by 4 so that the limit be equal to 1, because I want the sign, whatever comes after sine has to be on the top and the bottom. So it was 4x after, I need to have 4x on the bottom. You're allowed to multiply the bottom by a constant as long as you do it to the top. All right. This whole thing here is equal to 1. 1 times 4 is 4. All right. Now let's look at this one. All right. Same sort of deal. And what I'm going to do, and you could have done this for this other one too, but let's start doing it with this one. Sine of 3x, I'm going to separate the tops and the bottoms. All right, I'm going to separate the top and bottom. So I want this to be equal to 1. What would I need to multiply on the bottom for this to be equal to 1? Well, whatever comes after the sine, 3x, needs to be on the top and the bottom. So let me put this in a different color. If I put 3x on the bottom there, it's now equal to 1. All of that is 1. But you can't just do it on the bottom there. You have to do it on the top as well. The x's cancel, and I'm left with 3/5. And there's my answer. You'll notice 4x over x, the answer was 4. 3x over 5x, the answer was 3/5. And whatever you think by looking at the problem, the answer is, that's probably what's going to be, but you need to show this work. All right. All right. Apparently, I wrote the exact same problem down twice, but what I wanted to write, it was supposed to be sine of 3x over sine of 5x. Sorry. So it's sine of 3x over sine of 5x. So what you think the answer probably is going to be the answer, which is 3/5. However, you have to show why. So we're going to split up. All right. Put sine of 3x here. We're going to put sine of 5x there. I'm actually going to put a third one in here. All right, you'll see why. So I want this to equal 1, which means I need to add, I need 3x, so I need a 3x on the bottom. Here, remember, because it's either x over sine x over x or x over sine x. So this would need a 5x. So all this equals 1. That equals 1, but I have to put a 3x on the bottom. I need a 3x on top. I put a 5x on top. I need a 5x on the bottom. The x's cancel, and there is our 3/5. All right, so we're just manipulating the equation to make it the limit equal to 1, and then going from there. All right, last one is with tangent. Now, if you remember, what is tangent? Tangent, this property is only good for sine and cosine. So tangent is sine over cosine. So I'm going to rewrite tangent of 5x as sine of 5x over cosine of 5x. But there's already x on the bottom, so sine of 5x over cosine of 5x. Right? And what I'm going to do, I'm going to separate the two. Sine of 5x, x of cosine 5x. It only works for sine, not cosine, so it can only do this one. And have to add a 5x on the bottom. Now this is all equal to 1. All right, that's all 1. It's gone. But I put a 5x on the bottom, put a 5x on the top. When this happens, I can cancel out those x's. And I'm left with 5 over cosine 5x. And since I cancel something out, I can now substitute in 0. 5 times 0 is 0. And I'm sure you guys all remember what the cosine of 0 is. 0 in the unit circle is over here. It's 1 comma 0. Cosine is x, so it is 1. So I get 5 over 1, which is 5, which you could have guessed by looking at the problem, 5x over x. The answer would be 5. But you have to show this work in order to get full credit. All right. So you can now be able to finish the worksheet that we had done before. All right. That I assigned for homework the previous night. And like I said, we'll now spend the next couple class periods just practicing a bunch of different types of these. All right. The trig ones always, they trip up kids in the beginning a little bit. Then once you figure it out, it's not bad at all. So, don't be too stressed if you're not picking up right now after this video. Hopefully, once you get back in the classroom and I'm explaining it in person, you guys will have a little better understanding if you're not understanding it now. All right. Hope you guys enjoy the rest of your day, and I'll talk to you tomorrow.